You may have probably heard the term Max Q before during rocket launches, but what is it? What does it mean? What is Max Q? Hi. Welcome to Voxel, where we talk about all things SpaceX, space and rocket science. And today, we will be asking what is Max Q. Max Q is simply the point during an aerospace vehicle's atmospheric flight, where the dynamic pressure, Q, is maximum, hence the name. Dynamic pressure can be thought of like the equivalence of drag on a car, but for rockets. It is the point during the flight where the rocket undergoes maximum mechanical stress, and it is usually the maximum stress the rocket will feel during its entire flight. Dynamic pressure is a significant factor to be considered when designing aerospace vehicles, because the vehicles have to be strong enough to withstand the load during that time. Dynamic pressure, Q, is mathematically defined as: this is the air density around the rocket or how much air there is around the rocket, and V is the velocity. When a rocket lifts off, its velocity is zero, and the air density is at the maximum because density decreases as we go higher up, so the total dynamic pressure is zero. Similarly, when a rocket is in orbit, its velocity is maximum but the air density is zero, so the dynamic pressure is still zero. So we start with zero dynamic pressure on the launch pad because the velocity is zero, and end with zero dynamic pressure in orbit because the air density is zero. But somewhere in between these two states is where Max Q occurs. During liftoff, the rocket's speed increases, while the air density decreases. As the rocket moves, it pushes the air in front of it out of the way. And as velocity increases, the air can't move fast enough out of the way, so pushing air out of the way becomes more difficult. Due to Newton's third law, the air the rocket pushes out of the way creates an equal but opposite force on the rocket. Hence dynamic pressure. As the velocity increases, air pressure decreases because the rocket is higher up. The increase in velocity increases the dynamic pressure, but at the same time, the decrease in air density because of elevation reduces the dynamic pressure. However, the increase in dynamic pressure due to the rocket's velocity is much higher than the decrease in dynamic pressure due to the decrease in air density, so there is still a net increase in the dynamic pressure the rocket encounters. So there comes a point where the dynamic pressure becomes maximum. This point is termed Max Q. Above this point, the effects of decreasing air density start to win over the effects of increasing velocity, which causes the dynamic pressure to decrease rapidly. Plotting a graph, we get something like this. And the reason velocity has a greater effect on dynamic pressure is because velocity is squared in the equation. Meaning if the velocity doubles, the dynamic pressure quadruples. For example, SpaceX's Falcon 9 experiences a max Q of about 0.3 atmospheres, which is about 30 kilopascals or about 0.3 kilogram force per square centimeter, at approximately 11 to 15 kilometers of altitude. But you may think, the atmospheric pressure on the ground level is 1 atmosphere. Above 3 times that. Well, why does the rocket not explode at the launch pad? Well, because at the launch pad, the velocity is zero, so total dynamic pressure is zero. But at Max Q, Falcon 9 travels at about 2 km per second or 6,500 km per hour. And also, atmospheric pressure is not dynamic pressure. Atmospheric pressure is the total pressure of air, which includes static pressure and dynamic pressure. On the launch pad, the static pressure may be 1 atmosphere, but the dynamic pressure is zero. At about 13 kilometers, the static pressure is about 0.16 atmospheres or about 16.2 kilopascals, so its dynamic pressure at Max Q is about double the static pressure at this altitude. Max Q usually occurs about a minute into the launch of the vehicle, 1 minute and 22 seconds in the case of the Falcon 9. And although it varies, it typically lasts for about 10 to 30 seconds. But these few seconds can be the difference between a successful launch and a spectacular explosion. One thing to clarify, Max Q is technically an instantaneous event. But we can still refer to it as a period, the period at which the rocket takes some precautionary actions during this time. The Max Q region refers to the period of flight time at which Max Q will occur. How do rockets overcome this? Rockets are unstable vehicles. One wrong move and it goes down. Rockets are also not very strong, structurally. They aren't made from the toughest material available, because rockets are designed to be as light as possible. The Falcon 9 uses an aluminium-lithium alloy for its first-stage propeller tank walls. Other companies such as Rocket Lab's Electron rocket is made from a lightweight carbon fiber composite. Increasing a rocket's weight means it needs more fuel to propel that extra weight, which means it has even more weight and needs even more fuel and, you get it. Heavy rockets also limit the amount of cargo they can carry to orbit. For this reason, max Q is typically the most dreaded point during a rocket's flight. And the rocket is very susceptible to high pressures during this time. If a rocket cannot withstand, the rocket will break apart. So to overcome this, rockets typically employ quite a simple solution. They throttle down their engines during this point, to about 80 to 60% of their original speed to reduce some of that velocity and reduce the dynamic pressure. Rockets slow down their rate of acceleration, to delay the point at which max Q will occur until they reach thinner air where max Q will be considerably less. If they did not throttle down, they will reach a velocity that induces max Q a lot sooner where the air is a lot thicker and the max Q they experience will be a lot greater. Another reason max Q is so dreaded is that a rocket does not completely fly vertically. They start vertically but eventually tilt horizontally at some point. They tilt because the rocket needs to get to orbit. The rocket flies vertically just to get to the right altitude. Rockets need to go horizontally at incredibly fast speeds. Tilting the rocket early allows enough room for the rocket to get to that speed without exceeding its orbit. Tilting the rocket just happens to occur at the same time as max Q. Since the rocket is tilted during max Q, there is more rocket surface area on which the dynamic pressure acts, the sides of the rocket, rather than just the tip of the rocket. And the rocket is easier to break in half horizontally than to break in half vertically. So throttling down during this point is essential. And after the rocket has passed this zone, it can throttle back to full speed. That's just some of the insane science and engineering rockets have to go through to get to orbit. If you liked this video and found it informative, consider liking and subscribing.